Waveform-Based Gearbox Analysis, Time Waveform versus Spectrum Analysis, comparing techniques to evaluate gearbox conditions effectively. Why time waveform analysis is critical in gearboxes. Gearboxes are complex mechanical systems where multiple rotating elements interact simultaneously, producing vibration signatures that can be challenging to interpret using a single analysis technique. Traditionally, spectrum analysis has been the primary tool used in condition monitoring programs because it clearly identifies discrete frequencies such as shaft speed, gear mesh frequency, and their harmonics. However, spectrum analysis inherently averages vibration energy over time, which can mask short-duration events that are critical for early fault detection. Time waveform analysis directly displays vibration amplitude as a function of time, allowing engineers to observe transient events as they occur during operation. In gearbox applications, each tooth engagement produces a distinct pulse in the time waveform, and defects such as cracked, broken, or spalled teeth modify these pulses in characteristic ways. By observing the waveform, engineers can see exactly when abnormal impacts occur relative to shaft rotation, providing direct insight into fault location and severity. This approach is particularly valuable during the early stages of damage, when overall vibration levels may still be low and alarms based on RMS or spectral amplitudes may not yet be triggered. Time waveform analysis also enables intuitive interpretation, as it closely represents the physical reality of mechanical impacts and load variations. When used alongside spectrum analysis, waveform analysis significantly enhances diagnostic confidence, supports proactive maintenance decisions, and reduces the risk of unexpected gearbox failures. Limitations of spectrum-only diagnostics, spectrum analysis versus time waveform analysis. Spectrum analysis transforms vibration signals from the time domain into the frequency domain, making it highly effective for identifying steady-state, periodic vibration sources such as imbalance, misalignment, and gear mesh frequencies. In gearbox analysis, spectra are commonly optimized to highlight gear mesh frequency and sidebands, which can indicate modulation caused by load variation or misalignment. However, this transformation process averages vibration energy over the entire acquisition time, which reduces sensitivity to short-duration, high-impact events. Localized gear faults such as cracked or broken teeth often generate brief impacts once per revolution, and these impacts may not significantly elevate spectral amplitudes, especially in the early stages of damage. As a result, the spectrum may appear relatively benign even though physical damage is present. Time waveform analysis addresses this limitation by preserving the temporal sequence of events, allowing engineers to directly observe these impacts. The waveform reveals pulse spacing, amplitude variation, and transient behavior that are otherwise hidden in the spectrum. This makes it possible to differentiate between distributed faults, such as wear or misalignment, and localized defects affecting individual teeth. Understanding these limitations reinforces the importance of using waveform analysis as a complementary diagnostic tool rather than relying solely on spectral data for gearbox condition assessment. Understanding amplitude versus time representation, fundamentals of time waveform analysis. A time waveform represents vibration amplitude plotted directly against time, providing a real-time view of how mechanical forces act on a machine. In gearbox analysis, this representation is especially powerful because it allows engineers to correlate vibration events with physical processes such as shaft rotation and gear tooth engagement. Each revolution of a shaft occupies a defined time interval, and within that interval, individual tooth meshes appear as a series of closely spaced pulses. By measuring the time between pulses, engineers can calculate the corresponding frequency and confirm whether it matches known forcing frequencies such as gear mesh frequency or shaft speed. Proper data acquisition settings are essential to obtain meaningful waveforms. The sampling rate, defined by Fmax, must be high enough to capture individual tooth impacts, while the number of lines of resolution determines how many data points are collected. A widely accepted rule of thumb is to capture 4 to 10 shaft revolutions with sufficient resolution to clearly observe each tooth mesh. When these conditions are met, the waveform becomes a direct diagnostic window into gearbox behavior, enabling precise fault identification that aligns closely with mechanical reality. Identifying normal tooth mesh signatures, observing gear tooth meshing in time waveforms. In a healthy gearbox, the time waveform exhibits a largely sinusoidal appearance with evenly spaced pulses corresponding to each tooth engagement. These pulses are typically consistent in amplitude, reflecting uniform load distribution and proper alignment between mating gears. When viewed over multiple shaft revolutions, the waveform should show minimal modulation and no distinct transient spikes. The spacing between pulses can be measured to determine the gear mesh period, and its inverse yields the gear mesh frequency. This direct relationship allows engineers to confirm that observed waveform features are indeed associated with gear tooth contact. Any deviation from this uniform pattern, such as alternating pulse heights or irregular spacing, immediately suggests abnormal conditions. Because waveform analysis preserves the sequence of events, it provides a clear visual benchmark against which faulted conditions can be compared. Establishing this baseline understanding of normal tooth mesh behavior is essential, as it enables rapid recognition of subtle changes that indicate developing gear problems. Once per revolution impact signatures, detection of cracked or broken gear teeth. Cracked or broken gear teeth produce some of the most distinctive signatures in time waveform analysis. As the damaged tooth engages, it generates a high-amplitude impact due to the sudden change in load transfer. This impact occurs once per revolution of the affected gear, making it easily identifiable in the waveform as a repeating transient spike. Unlike spectrum analysis, where this energy may be spread across multiple frequencies and appear insignificant, the waveform shows the impact clearly and unambiguously. By capturing several shaft revolutions, engineers can confirm the repeatability of the event and correlate it directly to the gear's rotational speed. The amplitude of the impact also provides valuable information about fault severity, with larger impacts generally indicating more advanced damage. This capability to both locate and assess the seriousness of a defect makes time waveform analysis an indispensable tool for diagnosing cracked or broken gear teeth before catastrophic failure occurs. Low-energy faults revealed in the time domain, spalling and surface damage identification. Gear tooth spalling is a surface fatigue phenomenon that often produces relatively low overall vibration levels, making it difficult to detect using traditional alarm thresholds. In spectrum analysis, spalling may not produce prominent peaks, particularly in early stages. Time waveform analysis, however, excels at revealing these faults by displaying a series of impacts spaced at the rotational speed of the affected gear. These impacts correspond to repeated contact between the damaged surface and the mating tooth. Even when peak vibration levels remain low, the consistent presence of these impacts in the waveform provides clear evidence of surface degradation. By examining the spacing and amplitude consistency of the impacts, engineers can distinguish spalling from other issues such as misalignment or lubrication problems. This ability to detect low-energy faults early supports condition-based maintenance strategies and helps prevent progression to more severe damage. Using waveforms as a diagnostic reference, healthy versus faulted gearbox comparison. Comparing time waveforms from healthy and faulted gearboxes provides powerful diagnostic insight. In a healthy condition, tooth mesh pulses are uniform, and any apparent variation is typically due to scaling or display resolution rather than actual mechanical differences. In contrast, a faulted gearbox shows clear deviations, such as isolated high-amplitude impacts, amplitude modulation, or irregular pulse patterns. These differences are immediately visible in the waveform, even to experienced engineers conducting rapid assessments. This comparative approach is especially useful during troubleshooting, as it allows analysts to visually confirm whether observed changes represent true mechanical issues or benign operating variations. By maintaining historical waveform data, organizations can track the evolution of gear condition over time, further enhancing the reliability of maintenance decisions. Visualizing impacts relative to shaft rotation, circle plots for gearbox diagnostics. Circle plots provide an alternative visualization of time waveform data by mapping vibration amplitude around a circular axis representing one full shaft revolution. Each point on the circle corresponds to a specific angular position of the shaft, making it easy to identify events that occur at the same rotational location. In gearbox analysis, a damaged tooth appears as a prominent peak at a consistent position on the circle plot, confirming that the fault is synchronous with shaft rotation. This visualization complements traditional waveforms by offering an intuitive spatial representation of defects. Circle plots are particularly useful when communicating findings to non-specialists, as they clearly illustrate the repeatability and location of impacts without requiring detailed frequency domain knowledge. Isolating gear-specific vibration sources, time synchronous averaging, TSA. Time synchronous averaging is a powerful signal processing technique used to enhance gearbox diagnostics by isolating vibration components that are synchronous with a specific shaft. By using a tachometer signal as a reference, TSA averages out non-synchronous vibration sources such as bearings, motor noise, and structural resonances. The result is a clean time waveform that emphasizes gear-related events, including tooth mesh impacts and modulation patterns. Although TSA requires careful setup and longer acquisition times, the diagnostic benefits are substantial. The resulting waveform makes subtle gear faults more visible and easier to interpret, particularly in complex machinery where multiple vibration sources are present. TSA is therefore a valuable complement to raw time waveform analysis in advanced gearbox condition monitoring programs. Integrating time waveform analysis into gearbox monitoring, engineering conclusions and best practices. Time waveform analysis provides a direct and physically intuitive method for diagnosing gearbox faults that cannot be reliably detected using spectrum analysis alone. By observing individual tooth mesh events, engineers can identify localized defects, determine fault severity, and make informed maintenance decisions with greater confidence. Best practices include configuring data acquisition parameters to capture multiple shaft revolutions with adequate resolution, establishing healthy baselines for comparison, and using waveform analysis alongside spectral techniques rather than as a replacement. When combined with advanced tools such as circle plots and time synchronous averaging, waveform analysis becomes a cornerstone of professional gearbox condition monitoring. Implementing this integrated approach improves fault detection capability, reduces unplanned downtime, and supports a more proactive and cost-effective maintenance strategy.